Good evening, all. Actually, I want to conclude with fluoroscopy as we started last week, the concluding section of fluoroscopy. By way of revision, we all know fluoroscopy is just the method of seeing real-time images of a body. That is, if we can continuously acquire images of a body with time, that constitutes a video. So that is the essence of radiograph. The essence of fluoroscopy, being able to get a real-time images of the human body, which we saw last time is also the system that is used in the television. Television we view is actually the fast acquisition of images. So our brain will just interpret them like moving, like a motion picture. Because they want to continue from where we stopped. Once again, we are going to be using the slide for last week. Oh, what is going on? Okay. 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 We saw all of this last week. The image intensifier, the most important part of the fluoroscopy machine. Of course, gradually being replaced today by a flat panel. Okay, let me just do a brief of on this stuff. We have a brief survey of what we did last week. The fluoroscopy, we said it is a real-time imaging of the patient, of the human body, with high temporal resolution. It uses TV technology, which provides 30 frames per second, but because of interlacing, we now have 60 frames per second, so that the eyes wouldn't perceive it as wouldn't constitute a flicker. So we saw the imaging chain intensifier, the image intensifier, the most important aspect, which is made up of the various parts that we saw. The output, the input phosphor, the focusing lens, then inside the input phosphor we have the photocathode, then the output phosphor, and so on and so forth. So the different layers of the input phosphor, the four major layers. Photocathode, the electronic optics. We saw the pin fusion effects because of the circular input phosphor, which is an image which throws its image on the rectangular, which throws the image on the output phosphor. So the curvature there is seen, is represented with this artifact in fusion. We went there to see the focusing lenses G1, G2, I mean the focusing electrode G1, G2, and G3. And of course, the electrons are accelerated to a very, very high potential from 2500, that's 25,000 to around 35,000 volts. So the output phosphor is there for us. We also looked at the conversion factor, which is the luminance of the input phosphor all over the exposure rate of the image intensifier. That gives us the conversion factor. It has to be high, but with time, it continues to wane because of old age. So also looked at the brightness gain, which has got to do with the magnification gain multiplied by electron gain. I would say the magnification gain has got to do with the area of the input all over the area of the output. So that gives us a magnification gain. And electronic gain is fairly constant, which is around 50 for all image intensifiers. And the magnification gain, so it is at the area of the output phosphor all over the area of the input phosphor. As d squared, the diameter of this one of the output phosphor squared all over the diameter of the input diameter of the input phosphor squared, sorry, over diameter of the output phosphor. So I will look at the modes of operation of a fluoroscopy machine, the normal mode of operation and the magnification mode. In the magnification mode, the magnification gain is reduced. In magnification mode, we have much more exposure because to get a particular exposure rate, we have to increase the exposure. I mean, the rate of exposure has to be increased for us to have a particular brightness on the output phosphor. So it is not encouraged, except there is need for it. So we look at the example of magnification, diffusion effect, and optical coupling has got to do with all the necessary electronics that we have in the image intensifier. I saw this last time when the video camera, the lag, which is a problem with some of image intensifier. That is, a particular image, the residual image disturbs an image. Residual image, you have the information from a residual image in a particular image that we are viewing. That is what constitutes lag. We want to avoid lag as much as possible, but it can be of benefit in some procedures like assume basically in DSA, digital subtraction and geography can be of a benefit there. I think we might have to see that not later. So resolution, we talked about the horizontal resolution being determined by how fast the electrons respond. It is influenced mainly by the bandwidth. The bigger the bandwidth of the system, the better the video resolution on the horizontal axis, I mean on the horizontal range. Whereas the other one, the spatial resolution in the vertical direction, is determined by the number of scan lines. So the more the number of scan lines used to scan an image, the better will be the video resolution in the vertical direction. So we have that. I also looked at how the image is formed on the screen. It's formed in a kind of a raster line. That's because then to summarize the first section. Today we are going to look at the second section, which starts with the flat panel digital fluoroscopy. The flat panel, as distinct from the image intensifier, is that the array, the electronics, or the solid whatever semiconductor used for this is flat. It doesn't have it's not circular. This one is circular for its reason, so that the electrons produced can be focused onto the the output phosphor. Because this is the output phosphor around this area. This is this. This is where the input and phosphor is. This has to be circular so that the focusing will be easier and to achieve the modification. So this presents with a problem called the beam fusion effect. But in flat panel detector, that is not available. We don't have that problem. So the flat panel uses the thin film transistor TFT that are rectangular in format. It also makes use of cesium iodide scintillator. And of course, they also have a photodiode that converts electrical energy to electrical signal, in the light energy to electrical signal. Of course, they said it will replace. It is already replacing. Of course, at this is second edition of pushback. In the third edition, of course, even today we have so many systems that use flat panel and detectors. So many fluoroscopy systems that use flat panel detectors. In fact, so many imaging systems. So many of them are going for flat panel detectors. Like so many CT, so many simulators today using radiotherapy. They use flat panel detectors. So look at some peripheral equipments on the periphery, not part of the imaging chain. And the first one we want to look at is the photosport camera, which is used to capture images. At times, the fluoroscopists, the radiologists might want to see a, a hard copy. Want to see a hard copy film, a hard copy image. So they stop the video part and they quickly capture an image using the photosport camera. Of course, this is an old system. In today's system, modern systems today, it is a digital photosports camera that I use. So it has a high resolution. Of course, the signal is digitized and stored in the past and can be printed on the laser printer if required. Then the other one is a sport pin. In the first two we have looked at, it is in the photo spot camera and the digital photo spot camera. The image form is after interacting with the image intensifier. After the image, let's maybe go back to the imaging chain. Let me go back. Okay. In the photo spot and the digital photo spot camera, the system is arranged here. So this is where a photo spot image is formed. This is the film. This is for the manual one, or rather the old one, in which we stop the image, we stop the video acquisition, and then of course we can do the two. The two can be acquired at the same time. But instead of that, because if you're acquiring the two at the same time, the radiologist is not concentrating on the the video part, but wants to concentrate on the film. So this one can be stopped to concentrate on this. Just get the image here, then look at it in detail. So the image here has interacted with the image intensifier. It's because of the interaction here, the image intensifier. So the image we're getting here would have gone through a lot of a lot of filtering, not filtering in a way, that's gone through a lot of processes. So many gain, electronic gain, quantum, electronic noise, quantum noise, and so on and so forth, is going to affect the image so that the image we get here will have so much noise. So, but when the radiologist wants to get something, so when the radiologist wants a better resolution, an image with a better resolution, then it goes for the sports film. So this sports film is attached in front of the II, the image intensifier. So it wouldn't have interacted with the image intensifier before getting image, but before the image intensifier, in front of the image intensifier. So this one is just a conventional radiographic and screen film. You just put the screen film there and then get the image straight up. So this one gives us a very, very good resolution, both in terms of spatial resolution and even contrast resolution. So if you want a very, very high quality image of a particular, maybe a radiologist is doing a procedure that requires, maybe he wants to get some particular detail from a section of the examination, if I want to go for spot film. Then the cine radiographic camera is also attached. It's also one of the peripheral equipment you can have in the fluoroscopy machine. I may use in cardiac studies, which can operate from the from the frame rate of 30 frames per second to 120 frames per second, or even higher. Of course, we need this very, very high frame rate to reduce lag. Because if you use a very slow, low frame rate, the contrast resolution will be very, very poor because it's going to suffer from so much lag. But if you increase it to 120 frames, so the images will be acquired at a very, very fast rate, such that the lag will be reduced to the minimum, to the various minimum. So for that, the senior radiography cameras are very, very high speed, rapid cameras that acquire their frequencies very, very fast. So fluoroscopy mode of operation, you have basically two main modes of operation. You have the continuous fluoroscopy, which uses the current of 0.4 to 0.5 to around 4 milliamperes. Then we have the display is at 30 frames per second. That it means for one frame, we are going to spend 30 milliseconds. This is, okay, let me stop this and just at the board. 30 frames per second. 30 frames per second. Or 30 frames per second. So in 1 second, we have 30 frames. As in 1 second, the images coming from a position will come at the rate of 30 times. To be expressed 30 times every second. But to remember what we said about clicker, this has to be done in an interlaced fashion so that it will appear that we are looking at, we are firing it at 60 frames per second. So it means that in 1 second, it means that for one frame, we have 30 frames 1 second. So one frame, I'm going to acquire that in 1/30 seconds. So I'm going to give us what? 10, 0, 0.10, 0, in 100, 3, and so on and so forth. So that one is going to be in 100, 0.03 seconds. One frame is going to be obtained in 0.03 seconds. Is what? 1, 2, 1, 2. 3, this is going to continue 0.333 and so on. So 0.33 milliseconds. So we are going to be left with 33 milliseconds for one frame time for one frame. So that's for normal fluoroscopy mode. That's a continuous fluoroscopy. And for the maximum legal limits is 10 röntgen per minute. And acceptable the maximum legal limit that it has to be. In fact, more than 80% of all fluoroscopy operations are done at this range, at the continuous fluoroscopy level. Just a very few when a patient is obese, or I think that is the major reason that one has to go for high dose rate fluoroscopy. When you have some obese patients that require a high amount of exposure, it is permitted legally to go up to 20 röntgen per minute, about 20 röntgen per minute. But because of fluoroscopy being a procedure that could lead to some deterministic effect, it is expected that the fluoroscopy machine should have an audible signal. In fact, there is another pedal for high dose rate. If one wants to move from continuous fluoroscopy to high dose rate fluoroscopy, the a pedal has to be activated. It has to be pressed, different from the pedal when the radiologist or the urologist, as the case may be, is doing a continuous fluoroscopy. So, like I said, it is one can go up to 20 röntgen per minute. Then pulse and fluoro. At times, for some heart studies, where there are so many vessels that are highly pulsatile vessel, that the pulse rate is very, very high. The rate at which maybe blood is flowing through the vessels is very, very high. I think they're like artery or so. Then we have to use pulse and fluoro. In pulse fluoro, it requires the use of short X-ray pulses, very, very short, for a um, at times, most times, the milliamperes, the current can be increased, but the series has to be very, very short. It has to be as short as possible to reduce blurring, to reduce lag. Like we said before, it is usually used, it is mainly used in vessels that are pulsatile, and these vessels, most of them around the heart region and so on. So, for example, if one wants to introduce maybe this thing, okay, wants to introduce a stent into, you have maybe a vessel that has blocked or so, want to use a stent to open it up. Of course, a catheter has got to be put in place there before introducing whatever I want to introduce. So in that case, pulse and fluoro should be used if it's available. Of course, it should be available. So you can have lower frame, very, very high frame rates of 15 frames per second, 7.5 frames per second. Sorry, I'm missing that up. That is for very highly pulsatile vessel. But you can also have some variable frame rates. If you don't require, if a particular procedure doesn't require the time to be very, very short, you can go as slow as 15 frames per second, or 7.5 frames per second. where this is, we can do this if we don't have a problem, if we wouldn't have a problem of blurring. If blurring is not going to be, it's not going to introduce any problem in the fluoroscopy procedure, then we could go for very small frame rates and see 15 frames per second, 7.5 frames. This is actually going to reduce the dose a great deal. So this is one of the dose saving techniques I use in fluoroscopy, where we don't need a very high resolution. We should reduce the frame rates as, as small as possible, because there are some other, even during the procedure, there are some parts of the procedure that will require very good contrast resolution. During those moments, then we can increase the frame rate, but for the ones that don't require very high resolution, then it is advisable to use lower frame rates. And frame averaging is also one of the techniques that is used to improve temporal resolution. Of course, low temporal resolution is the ability to depict objects distantly, even as they traverse the tissue. You have a system of flowing blood flowing through a vessel. At each point in time, if you get the image of that blood moving, if we can depict that at this point, this particular particle of the blood was at this particular portion of the body, then the stuff has very wonderful temporal resolution. That is, that machine has very temporal resolution. So one method of doing that is by using um, frame averaging. Averaging. Of course, we know that fluoroscopy images are noisy. Why are they noisy? Because we use very low dose to acquire them. Like we said in our last lecture, that for normal radiography, maybe radiography of the chest, the dose to the radiography, during radiography of the chest is just about, you can say about 1,000 times lower than those imparted in capturing one frame in radiography, in fluoroscopy. Thousands of times less than that is what is used in fluoroscopy. So because of that, there is going to be relatively huge noise associated with that. But at times it is beneficial to compromise the temporal resolution. We can make do with the temporal resolution for us to have better images with lower noise. That is, with good, with of course with a lower noise. So in that case, during such situation, we can use a frame averaging. In frame averaging, what happens is by assuming this is the frame that we should actually use. This frame here is the one that provides more of the information. So instead of using only this one, what the machine does is it uses some a number of frames, and at the end we average the information on these in this frame. So that's just the name, frame averaging. Instead of using one particular frame or just two particular frames to get a particular information we need, we average a much more number of frames. By doing that, we are increasing the we have reduced the noise. The image we are going to get at the end of the day will have a reduced noise. We're going to have a reduced noise. So this is an average. This is the average of all these images that have been captured. At the end of the day, we're going to have. So this is going to have a better what's it called? A better SNR, signal to noise ratio. But at the end of the day, we are going to have kind of lag. We'll have lag because this information, this is just an average of all the information here. So the information here will be superimposed on this, assuming you have an object moving in a particular vessel. If you had them taken this one, the object when it is at this point, we give a better um, depiction of its position. But because we want to see how we can improve the SNR, so if we want to improve the SNR at the expense of the temporal resolution, all we need to do is to average a number of frames and get on with a less noisy image. So this is done in real time by the processors in the computer. Of course, we have said it before, it can cause a noticeable lag. What is this? It can cause a noticeable lag, but noise is reduced, which can be beneficial at times. Of course, in some circumstances, those can actually be reduced. So we last frame hold. This is a very, very wonderful feature in all fluoroscopy machine. The last frame hold has to be there. How does this mean? For example, when one is watching, maybe one is watching a particular program on television, all of a sudden something happens. Everything, the TV goes black. It is not, it's not a good feature in fluoroscopy. In fluoroscopy, when the fluoroscopy is working and maybe something goes wrong with the fluoroscopy machine, instead of seeing a blank monitor, the last frame hold ensures that the last live image, the image that was captured last, will continuously be shown on the image on the fluoroscopy machine. That's on a monitor. So it is a very, very useful. For example, one wants to the radiologist wants to have a better look at that particular image. Maybe very advancing of the catheter through the body, or whatever. Got to a point where the fluoroscopist wants to see maybe the journey of that catheter, wants to see it in a more detailed manner, more detailed fashion. What to do is just engage the last frame hold, and stop there and look more intently at the image on the monitor. Of course, this is useful at the training institution, maybe for, of course, in teaching hospitals and whatever. We have a lot of doctors in training. It is useful there because at that point they want to experiment with the machine and so on and so forth. All they do is make use of the last frame hold so that the patient doesn't receive unnecessary dose. Because if the machine continues, if you want to look at that particular image, you want to look at the particular image, and the machine is still on, the patient will be overdosed without without any procedure, without any special thing going on. You are not looking at, you are not advancing the catheter. Maybe the radiologist has just stopped just to look at that. So nothing is actually happening, but we just want to look at a particular portion of the passage of the catheter. So it is a very, very good feature on our fluoroscopy machine. Then we have road mapping. Of course, it's a kind of last frame holder feature. How is it? Right from the road, from the name, road mapping. In this road mapping, we have two monitors side by side. One of the monitors shows the image that has captured. and the other shows the live image. That is, one is, you can say that one is the stereo monitor, the other one is the video monitor. So the one for video shows the live image, while the other one shows the captured image. So at each point in time, we can always get a kind of a last frame hold on the first monitor. Because that one continuously displays the still image, while the other monitor displays the advancement of whatever, maybe the contrast we've given. We want to see how the contrast and spreads throughout the body. And the other one shows the last frame. If at another point in time you activate the last frame hold again, it shows you the most current picture on the first computer, which shows the captured image. At every point in time, you just press the last frame hold on the first computer. It shows the last image captured, and so on and so forth. At every point in time, and see our last image, and then also we continue to see on the other video, on the video monitor, how whatever we are doing is advancing, maybe the catheter we are doing or whatever, radiotherapy, how the things, what's it called, the seeds, the radioactive seeds are being implanted into the body. In angiography, subtracted image can be overlaid over the live image to give the angiographer a vascular road map on the fluoroscopy image. I think, okay, let me stop this and look at that. During the road mapping stuff, road mapping I think is mostly used in a DSC, digital subtraction and geography, whereby all the other vessels, all the other tissues have been subtracted. Just we are left with the um, the blood vessels and so on and so forth. So during road mapping, all we need to do is we have an overlay of, let's say, this is the vessel. Let's say the blood vessel. The blood vessel is captured as a last frame hold. Then this one will now serve as a roadmap. It will now serve as a roadmap. The image will be there. It will be there on one computer. And this one is just a one computer. Then when the other now begin to advance the catheter through the vessel, because you will now be seeing it as you are moving, as you are introducing the catheter and so on and so forth. So this one will serve as the roadmap. The image of the what's it called? The image of the vessel that has been captured initially will now serve as the roadmap for the catheter we have introduced. It can also be whatever. It can also be the contrast that has been injected through the vein. Okay, let's continue with the screen. We saw here, or as we have seen here, in angiography, subtracted image can be overlaid, like I just said. I think it's digital subtraction angiography. It's used for advancing catheters through very, very tortuous vessels that are very, very difficult. They have a very, very difficult terrain, using sand and so on and so forth. So road mapping is very, very important. Very, very important here. Then we'll now go to automatic and brightness control. but the term has slightly changed these days to still ABC. No, still okay. Well, it's still ABC in a way. So it is of course at the output post for there is a particular brightness that has to be maintained, and this is done the by the generator of the machine generator. It is triggered by changes in, we have so many combinations. So the ABC controls the KVP and the MA of both of them. Maybe for a particular patient, the ABC circuit might use a particular arrangement, I mean, particular combination of the KVP and then MA. For another patient, it looks at the patient's, of course, because of the sensor there, and now brings out a particular approach, I mean, a particular protocol for that particular for that patient. So the automatic brightness control does that, which we also see in radiography and radiography. So this is just the code that explains automatic brightness control. We have the upper code, which in this one, the higher dose. This one changes in MA, more change in MA causes um, causes this. I mean, the first curve here, we have two curves here. For a thin patient, if you increase the MA, the rate of increase of the MA is greater than the rate of increase of the KV. But for this lower curve, it has to do with more the rate of increase of the KV, of the KVP, and the potential is greater than that of the MA. So this has got to do with if you want to manage the contrast resolution, you you want to change that based on the MA. So a little increase in this MA is going to affect a better contrast, better than a KV. So the KV wouldn't have so much effect in increasing the contrast here. The much of the contrast has got to do with the MA. Is going to determine how good the contrast is going to be. But this one is a KV is basically meant for lesser dose. If you want to lower the dose, of course, as we are lowering the dose, we are getting lesser contrast. The lower the dose we use, the lesser the contrast we are using. That is, if we are increasing the KV, we are lowering the dose, and of course, we are getting um, the contrast by increasing the KV. So this for a thick patient. The thick patients require higher dose and a higher KV, whereas the thin patient requires a lower dose, a lower MA and a lower KV. But the machine's ABC is what actually does that. If it looks at a particular patient, am I going to increase MA more than KV or increase KV more than MA? So he does the machine does the mathematics, the calculation, and does the right thing. So the top of increases MA more rapidly than KV. Because of the function of patient thickness, and the bottom curve increases KV more rapidly than MA. Of course, also depending on patient thickness and stuff. So image quality and spatial resolution. Of course, we continue to encounter spatial resolution as far as radiography is concerned. In all imaging modalities, spatial resolution is very key. It's an important parameter that we can't do without. We want to be able to know, to see structures. And spatial resolution has got to do with the ability to detect too closely situated structures. The two structures are closely situated, and the machine can depict them as two distinct structures. Then that machine has very good spatial resolution. If not, it doesn't have. So the ability to depict that constitutes some spatial resolution of the object of the machine. So we have and width have a spatial disbalance because we have the lateral spatial resolution and the axial resolution as in the top down top down whatever top down direction gives us the axial, whereas the horizontal direction gives us the lateral resolution. The two of them actually constitute the spatial resolution. We have encountered that earlier. So it's just the ability of an object, of the machine, of the system to depict two objects as they become smaller and smaller and smaller and closer together. So the closer they are, we may still showing them as separate objects, then the better the spatial resolution of that object. So as the objects become smaller and smaller, and the machine is still able to get them as separate entities, then it has a wonderful resolution, a wonderful spatial resolution. So at some point, the two objects become so close that they appear one. At this point, spatial resolution is lost. That is the limiting spatial resolution of the machine. At the point where spatial resolution is lost, that is the limiting spatial resolution of the machine. So and the spatial domain simply refers to two spatial dimensions for an image, the x dimension and the y dimension. Of course, you look at the x dimension as I think the x dimension has got to do with the, okay, let me see that on the board again. Let's see it on the board. The x dimension. The x dimension, the y dimension, the x dimension, the y dimension. The two objects along this way, and the machine can distinguish them. Maybe two objects. Have two objects. The machine can still distinguish them as two distinct objects, two distinct structures. Then such a machine has a wonderful spatial resolution. In this case, this lateral x, lateral resolution. And for horizontal resolution, if the two objects are, it is the imaging plane, and the machine can depict them as two separate objects, two separate structures. And that machine has a wonderful axial resolution, that's X plane, axial resolution. That's a wonderful axial resolution, that's Y plane. So at the end of the day, these two, both lateral and axial resolution, constitutes whatever a lateral, what's it, a resolution, a spatial resolution, sorry. Lateral and axial represent, they constitute a spatial resolution. Let me continue with the screen. Okay. Okay. So the line pairs a special frequency. A special frequency is the line per millimeter. What do you mean by this? The line per millimeter. If an object has for a big object, the line per millimeter, this is the size of the object. is just 1 over 2 times the size of the object. So smaller objects that have, of course, a smaller delta, they correspond to high spatial frequency, and larger objects correspond to lower spatial frequency. What this means is for smaller objects, they should have the imaging modality, the imaging system, the machines you have should be able to resolve them. And for it to be able to resolve them, it has to have a high spatial frequency. Whereas for larger ones, they require lower spatial frequency to be able to distinguish them very well. For smaller objects, the smaller an object is, the higher the spatial resolution that is needed to be able to distinguish it correctly from an adjacent structure. But the larger the object, the smaller the spatial resolution that is required. So we just we look at this for an object that is 0.36 millimeter, it just corresponds to 1 all over 2 times 0.6. At the end of the day, you're going to have a 1.4 line per millimeter. For one which is smaller, this one is smaller, so it requires a bigger spatial resolution. I mean, a bigger line pairs per millimeter. That is spatial frequency. It requires a bigger spatial frequency for it to be accurately determined. For this one, which is the biggest, which is 0.1 millimeter, corresponds to 0.5 line pairs per millimeter. So this is the biggest here. It requires very small spatial frequency to be able to accurately determine it. So the bigger the object, the smaller the line per millimeter required. That is, the bigger an object is, the smaller the spatial frequency. But the smaller the object, the higher, the bigger the spatial frequency. So look at of course, so we just look at the spatial frequency, just another way of thinking of object size. We have this bar resolution quantum that is used to measure spatial resolution. So we have that. As we know, the bigger as we increase the diameter of the field of view, I mean the diameter of the image intensifier, we need the line pairs per millimeter reduces. So for this small one with small frequency, it requires the spatial frequency is very, very high. You can see that. So for 20, it doesn't require so much a resolution like the one of 2.7. I mean, the one of 20 doesn't require so much of resolution than like the one of 14. So as the image intensifier increases, it becomes bigger. There is a little, there is, not so much is placed on the spatial resolution. I think we'll get to this. Okay, let's look at this object. This diagram. For this diagram, this MTF, resolution transfer function, as against spatial frequency. Of course, the resolution transfer function is, in fact, it is the best function that is used to analyze the image and performance, as is the image quality of the machines. The machine that has MTF, a very high MTF, is a very good machine. In terms of spatial resolution, that machine is a good performer. I look at this object, but look at the MTF reduces as the spatial frequency increases. What do we mean by this? Okay, we look at spatial frequency of 1. What does it correspond to? Okay. Let me draw that on the board and see how we can make a little. Draw two. Okay. Oh, 5259. 2.9. This is 1023, 1023. This is image intensifier. This is an optic subject. This is an optic. This is an okay. This is a one. Two. Special frequency. Special frequency. Circles per millimeter. Some per millimeter. These are ACF and TF. Okay. As the case may be. Okay, let me share the board with us. So we look at this. I want to look at the relationship between MTF and special frequency. This special frequency of 1, you can see as the special frequency increases, the MTF reduces. So what does that imply for us? What does that imply? So it means for this that has a special frequency of 1 cycle, 1 second per millimeter. What does that mean? It means 1 all over 2 this equals 1. And this is a special frequency, 1 all over 2 delta. Delta is the dimension of the object we are looking at, the structure we are looking at. So for if we have an object which is 1, it means 2 delta times 1 is 1. At the end of the day, the depth of this 1 over 2, which is at 0.5, 0.5 millimeter. So this 0.5 millimeter is, for this, MTF is this value here. For this, MTF value is this value here. For this one, MTF is this value here. So for an object which is a 0.5 millimeter, it is the II, an image intensifier system, is going to give us the best resolution of that object because it has the highest MTF with vision transfer function. But for an object which uses how many lines? 1023 lines to form the image. It is going to have something around the 70 something based on the information we have here. Then for a system which uses 525 scan lines, the resolution, the contrast is going to be reduced in terms of MTF. MTF actually gives us a contrast. So that's, so you see our II is about is better than all of this. Then this one is for what's it called, optics, and then this film. Film has excellent, very wonderful spatial resolution. That's why it is a very close to 100. Then we go to 2. An object whose spatial frequency is 2. So it means that 1 all over 2 delta is 2 millimeters. 2 millimeters, 2 seconds per millimeter. So 4, 2 times this, 4, this is 1. So this is going to give us 1 all over 4, which is 0.25, 0.25 millimeters. So this 0.25 go the same way. This one goes here, this one here, this here, and so on and so forth. So for an object which is 0.25, it requires a system with a particular um, spatial resolution. It places so much a burden on that system in terms of spatial resolution. So because a particular system has fixed and spatial resolution, a particular system has a fixed and spatial resolution. So the spatial resolution wouldn't generally increase, except you want to increase maybe the matrix size and as the case may be, so on and so forth. But it is somewhat fixed. So for an object which is at 0.25, on the machine we have reduced spatial resolution because this one requires much more better resolution than this one, which is at 0.55 millimeter. So because of that, we see that the spatial resolution continues to increase as as the object diminishes, as the size of the object diminishes, spatial resolution continues to decrease. It is decreasing this way. So as the object becomes smaller and smaller, the spatial resolution continues to decrease until it gets to a point where it is almost zero. At this point, for this machine, the limiting spatial resolution is around here. You can calculate that using this formula to get the limiting spatial resolution. I mean, the limiting spatial resolution for this machine is around 3. Maybe this one's around 3 or 5. So this one is around 3 cycles per millimeter. This one is around 5 cycles per millimeter. This one maybe around 6 cycles per millimeter. So we can see from the graph that as the object becomes smaller and smaller, the spatial resolution continues to decrease. So it places so much a burden on that system. So it gets to a point where you wouldn't be able to distinguish the objects correctly again as their sizes become smaller and smaller and smaller. So let's continue with okay. How's it? Okay. Okay. So the MTF illustrates the fraction represented on object contrast that is represented by the imaging system as a function of the size. The function of the size of the object. So the limited spatial resolution is the size of the smallest object that an imaging system can resolve. Of course, we saw that the limited is the size of the smallest object. Like this, for example, the size of the smallest object is that which corresponds to a spatial frequency of 2 cycles per millimeter. So at the end of the day, we see that the size of the smallest object, which this 5-2 line TV camera can resolve, is you see on the board again, 1/2 is a 0.25. For this one, it is a 0.25. That is a limiting spatial resolution. I mean, the limiting size of the object it can resolve. So the limited resolution of a modern image intensifier is between 4 and 5. Between 4 and 5, which is pretty good. Contrast resolution. Of course, contrast is the ability to see structures as distinct. You have 2 structures, 2 different structures. The ability of the system to depict those structures as different is contrast resolution. So if you have a lung, if you have heart, if the system can distinguish lung differently from heart, then it has a good contrast resolution. So it is related to the amount of noise. The more the noise in an image, the lesser the contrast resolution. That is why at times If you want to increase the contrast resolution, increase the exposure constant, exposure rate. Increase exposure rate, it means one is using much more photon in acquiring the image. And what that means is there will be less statistical variation in the number in the quantum, I mean in the photon used. So that's otherwise means we have a high SNR, signal to noise ratio, or even CNR, contrast to noise ratio. So better resolution implies that more subtle objects can be routinely seen on an image. So computer is slow by comparison to radiography. In no respect, it is low. And because of the low exposure, the results are involved. Of course, you can increase contrast resolution by increasing the exposure rate, but this is at a price, and the price is a more radiation dose to the patient and even to the radiologist also by way of scatter radiation. The more they do to the patient, the more they scatter, the more the dose that will come to the fluoroscopists, the radiologists, the urologists, and so on and so forth. We let's look at some examples of the noise contrast and the relationship. We look at a particular image here, a coronary angiogram. We acquired at 2 microröntgen per frame, and the angiographic one, the other one is a 16 microröntgen per frame, 2 different exposure levels. This one is 2 microröntgen per frame. This one is a 16 microröntgen per frame. You can see the difference. This one is very, very grainy. It is grainier than this other one. So you can see that. So the noise here is lesser. The noise here is 16 microröntgen per frame is lesser than the noise here. We also want to look at the digital imaging quality. When it comes to digital imaging, metrics has a lot of effects. The metric size has a lot of effects. We have this particular diagram. This particular image was captured with 512 by 512 matrix. Matrix is actually the number of elements, elements used in particular image. The 51, let's say 5 by 5112 by 5112, it means the horizontal axis we have 512 distinct lines, and in the vertical we have 512 distinct lines. This way, you continue having distinct lines 512, and along this way we have 512 distinct lines. So this is going to give us a very, very good contrast resolution compared to one that we're using 256 by 256 as the case may be. So let's go to the okay. We have 256 by 256. This gives us a good contrast. The contrast here is not as beautiful as the contrast here. So that's the effect of matrix at the matrix side. The more the matrix side, the better the contrast resolution. That's the better the CNR, that's the contrast to noise resolution, and also SNR, signal to noise resolution. You can see 28, 128 by 128, something has been reduced, becoming very, very blurry, not sharp any longer. Okay, we now have a 64. You can see that has become almost skewed. Also look at the gray level. Gray level is the number of bits that is used to store an image. Number of bits used to store an image. If you use 8 bits, then we are looking at 256 gray levels. 2 bits actually means 2 raised to power 8. 2 raised to power 8 will give us 256 bits. If you have 2 raised to power 8, that's 2 times 2 times 2 times 2 times 2 times 2 times 2. I'm going to give us the 256 degree levels. So this one can also give us a kind of a resolution. Of course, we have to if we want to compare it with another one that uses another gray level, then we can speak. But for now, we just know that this one uses 256 gray level to store this information or to acquire this information. So if we look at another one that uses a 4 gray level, this is a 2 raised to power 2, 2 times 2, 4. And we compare this one that is using 8 bits. This one using 2 bits, which corresponds to 4 gray level. This one used 8 bits. You can see there is so much more distinction of the structures here. The structures here have a very, very high contrast. You can differentiate this from this, so on and so forth. These three objects here, they are distinguishable. But we go here, look at, they have been modeled up here because we are using just a 4 gray levels for the same matrix size. Of course, one condition, one factor has to be kept contact for us to be able to look at the differences that will then come up when we vary the other factor. So we now also look at temporal resolution. A fluoroscopy, we know it has very, very wonderful temporal resolution. Temporal resolution is not the resolution of the resolution as due to time. Um, if you have a you have a video or you are monitoring the introduction of the catheter in a vessel and you want to monitor its motion of that catheter at every point in time. You're monitoring it via a video monitor. The monitor inside the fluoroscopy room. If that machine can give us maybe the position, let me use a contrast now. The position of that contrast at every point in time. That is representing the contrast as it moves on. And if the representation is such that the position of that contrast at any point in time is the actual position in the body, then it has a good and temporal resolution. But if it is not, then it has the bad temporal resolution. So this has what to do with the lag. If an image, if a video has so much lag, and it means the temporal resolution is very, very low. Of course, this is the problem with not the problem with Zoom. If you are using Zoom and the bandwidth is not so high, it's not so much, if you continue to see lag, of course, it is not only the bandwidth, it's so many factors that come to play there. The camera the camera and pixel size has a role to play. The monitor or the system one is using also has a role to play because they have their own resolution. So blurring is typically a problem with temporal resolution. If you have blurring in a particular video, then it means the temporal resolution is bad because the information of a particular event is carried over to the next event. So I imply the person will be for me if you can be able to so if you get a message or if you can demonstrate the payment of but a full beacon video, the lag is much more reduced. You can see lag in general is undesirable, except maybe for digital separation in geography, where lag can actually be a kind of a roadmap to leave a trailing end. The trailing ends when the catheter is being introduced. Continue to see it. And the something is we continue to see the image, the um, the image of the previous, or let's say, you can see that with the image of the previous frame. You see it in the next frame, part of it. So it is not a problem for BSA. but in every other thing, it's not a good way. Frame averaging improves control at the expense of temporal averaging. We have said that before. With DSA and digital cine, camera with low light performance could become, like we said before, the other time we talked about the Rubicon, and not as a wonderful as a Rubicon when it comes to low light and performance. Um, Fluoroscopy suites, we have so many of them. These are a geographic fluoroscopy system. It depends on the institution and what the procedures they want to be involved in. To determine the type of fluoroscopy suites that they need to put in place. We have some of them. We have the GI suite as an area. The II is above or under the table. Spot being visually there. But in most it is always advised that as much as possible, we let the X-ray tube be under the couch, already for protection purposes. As much as possible, if it is possible, always make sure I mean the what's it called, the tube, the X-ray tube is under the table, so that the lead apron and drapes that are used protect the photograph, I mean the radiologist very well. But in some cases, we don't have option, but for depending on the procedure, but for the stuff to be up, the tube to be up. In that case, of course, there should be serious sensitivity. I remove fluoroscopy, the fluoroscopist, the physician, the radiologist, the neurologist, and specifically, I just in another room with the lead glass separating them and the wall and every other thing. Also, just like we have in other modalities like in CT, like in MRI, where the machine is in another room and we have the photographers and so on in another place. And the kind of remote. If it were possible, one fluoroscopy machine, I mean, one fluoroscopy intervention to be done in the remote rooms, of course, to be very nice and good. But in most cases, it's not always possible. One is undergoing an operation, and the operation is being operated upon, and want to be seeing the real life procedure at some point in time. Then the whatever, the orthopedic surgeon, the neurosurgeon, the fluoroscopist, or whatever, they have to be in the room. They have to be in the room to do, except they want to use a robot to do the operation. And they can continue to operate the robots from a remote room. Or if not, they have to be there. These are some geography system. Paper and geography suite is also the very close how to apply the bigger the outline use. For category categorization suites similar to what you want to use. Now the biplane. The biplane geography suite. This one has two tubes, two X-rays, two X-ray tubes, two image intensifier. And this during this one, this is not the biplane mode anyway. It does not have the graphic system. During with the biplane mode, you'll be acquiring APPA posterior, anterior, and anterior posterior at the same time you're acquiring the lateral view. So now the portable fluoroscopy, which you have in so many institutions, C-arm. So an example of a C-arm. C-arm. You can see the shape C. So that's why it is called C-arm. Very portable and we use for some limited interventions, and not the very complicated ones that would need a dedicated fluoroscopy machine. So this one can make do with so many interventions. Relation dose, a patient dose, maximum limit, we know it is 10. When that one is exposure, of course, from there you can actually calculate the exposure, the dose rate, I mean the dose. This one is 10 ranging per minute for continuous fluoroscopy. That's another fluoroscopy. Then for special activated fluoroscopy, you can go high to 20 ranging per minute. But the bottom of the there, the pedal must sound immediately. One is using an activated fluoroscopy. You continue to hear the sound, so on and so forth. To alert the doctor, the fluoroscopist, the neurologist, as the case may be, that you are using the special activated fluoroscopy form. So one has to be careful. So we massive radiation dose, the thicker the patient, the more the scatter, the more the entrance skin uh, exposure. But then, as it continues to reduce, it increasing kV. And kV increases, it reduces. I mean, yeah, it reduces and the kV increases, but it increases with the patient thickness. The thicker the patient, the more ESC, entrance skin exposure. And is it? So those two personnel, I think at the term, standing 1 meter from the patient, the patient will receive scattered radiation on the outside of the apron. That's outside the apron, not inside the apron. But by the inside apron would have been attenuated by the lead apron. At outside of the apron, 1 meter, the fluoroscopist or observer as inside the room receive 1,000 of the exposure incident upon the patient, and it increases with um, increases with um, patient thickness. This height above the floor. And this is 100 cm here, 100 here, 60, 40. Height above the floor. This is for different patients. 20 cm. So we have those rates as a function of height above the floor is shown for 6 different distances. 6 different distances: 100, 80, 60, 40, 20, and 10. A distance from the patient. The further the person is from the patient, the lower the dose the personnel is going to receive. For 80 centimeters, you can see it continues to increase. Closer to the patient, closer and closer, 10 centimeters to the patient, going to receive very, very high dose. And again, the height above the floor is kind of follows a normal distribution. Normal distribution, it continues to increase up to a point, then it decreases. So at this point, the navel and the gonad, they are where at this point they receive most of the radiation. So one has to be careful. That's why it is best to have the X-ray tube under the couch so that the personnel can be protected. But if it is up, if the tube is up, it becomes very, very difficult to shield that room. It becomes a very, 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 very difficult shielding. So you can see now, if those increases when it gets to donor, then falls off gradually down this way. So we have the RAP meter, the DAP meter, usually attached to the fluoroscopy machine to measure the dose rates. So I think I've come to the end of this. These resources are also you go online to get them for that. Okay. further enlightenment. Okay, we have come to the end of today's lesson, which brings an end to fluoroscopy. I want to invite questions. If you have questions to ask, let's do that. But very soon we will move at a much more faster rate. Maybe after next week or so, upper week, the month of towards the end of the month. I think we have to go towards the end of the month, the last week of the month. We have to enter on a speed lane. So that is that for today. It brings an end to fluoroscopy. We still have some other very, very important topics as we go into, even before we enter mammography, what's it called? Ultrasound. We're looking at some of the topics that we further develop in this radiography. General radiography, as fluoroscopy, mammography, and ordinary radiography. In terms of image quality, we're going to briefly look at that next lesson before we now go over to, I think the next topic should be ultrasound. So I think ultrasound, of course, so many of us are familiar with ultrasound. It's an equipment that is not so costly that all institutions are meant to have. So I'll invite us to ask our questions. If you have any questions to ask, I think this is the time to do so. If you have questions to ask, if not, we are going to see how we develop, get a quiz on all these questions. I mean, all these topics we have raised so far. But that is going to come after the next series of lectures. What's it called? The next lecture, image quality and the likes. Before we go to mammography, sorry, before we go to ultrasound, we will then take our questions on this and general radiography that we have done. But we have questions. If you have questions to ask, okay.
Hello, sir.
Okay, can hear you.
I wanted to explain further when you talk about frame averaging and lag. Uh, the relationship, how does it cause lag? Frame averaging.
Oh, you can't say anything again. Oh, wow.
Can you hear me, sir?
Come again.
I said maybe you can explain the how does frame averaging cause lag?
Free.
Frame averaging.
Okay, frame averaging. How it causes lag. Okay.
And this spatial resolution. When you say that in a film has a better spatial resolution, and I understand it has a better spatial resolution compared to II.
Okay.
Maybe you can throw more light on it.
Okay. With respect to this diagram.
Yes.
Okay. Okay. Let's look at the frame averaging. I don't want to rub this one up. We'll still use it. In frame averaging, for example, you have you have five frame. Assuming the information one is looking for in a particular procedure lies with maybe mainly between this one and this one. And let's say this image. You have this one, and at this point, you have a structure that is appearing here. You have a structure. The structure is, and at some point in time, it's going to disappear. But in this one, the structure is not, this structure is not there. This structure is not in this particular frame because they are actually different events. It's actually so many, you can have maybe 100 frames in a particular minute or whatever. So this is what we are looking for. This frame is the one that captures the information very well. But if you use this, you're going to have low SNR, low signal to noise ratio. You're going to have low signal to noise ratio. Instead of that, if we want to improve this SNR, we can average these 5 frames. 1, 2, 3, 4, 5. When we now average them, the frame we are going to get is just the average of everything. So some of these things here will also appear here. But initially, if we had used this only frame, we're not going to have anything. So at the end of the day, you're going to have a kind of lag because we're actually looking at a motion picture. Something is done real time on the computer. It uses 3 frames. It averages 3 frames, gives the image on the monitor. Averages, you can average 10 frames, give the image on the monitor. So at the end of the day, as the motion, as this one is appearing, the next frame that appears again is an average of so many frames that have been used. So you're going to be causing kind of lag on the picture. As you are looking, you'll be having a kind of lag because the image that has been used is actually the combination of so many images. It's just the average of so many images. So at the end of the day, you're going to see that as a kind of lag. I don't know whether you got that.
Yes, I do. I do.
Okay. Then for film and then II, a film is up here in the NTF graph against spatial frequency. Look at this at 1 cycle per millimeter. At 1 cycle per millimeter. 1/2 and spatial frequency is equal to this one here. And 2 delta
How do
is
you come
1.
about 2?
Pardon?
How do you come about the 1/2?
So this is the formula for calculating spatial frequency. The spatial frequency
Okay.
is given by this 1/2 delta. Delta is just the object size.
All right. Okay.
So the spatial frequency 1/2 is 1, according to this graph. And then you're going to have 0.5 millimeter. So this is the at this level of a spatial frequency of 1, the object is 0.5 for you to have a spatial frequency of 0.1. But for II, it is somewhere around here. So II is not as wonderful in discriminating an object which is a 0.5 millimeter. The best this one can give maybe around 90 or so. But I feel we give close to 100 for that same object which is a 0.5 millimeter. If we go to 2, 1/2 is will give us 2 here. So 2 for this is 1. So this is going to give us 1/4, which is a 0.25 millimeter. So for an object which is 0.52 millimeter, this one is going to give us a particular value here. Not so wonderful like this. This one is not so wonderful like II close to around 80 based on this diagram. But film, you can see film give us around 90% MTF. So the spatial resolution for film is 80%. For all values, film has the greatest MTF, followed by optic, followed by the II, and so on and so forth. So that is how that is. The film has the best spatial resolution. in fact, of all imaging modalities, even for digital radiography. I don't know whether you got that. I was able to bring
Yes,
that.
I did. I did. Thank you very much, sir.
You're welcome. I don't have any other question before we call it a day. Please, if we have further questions at any point in time, we could just drop them on our site, and I mean our web, on our WhatsApp page. You can drop them there, and I want to believe some of us might have answers to the question. If not, if I have the answers, I will give. If not, I have other people that I can contact to help us out with any question. Oh, or if that's the case, I want to wish us.
Hello, sir.
Okay.
Hello, sir.
Okay, I'm
Sorry,
hearing you.
sir. Good evening. Yes,
Good evening.
I'm sorry I joined late. I'm on call in city.
So sorry about that.
Yeah. Sir, this graph on the board, I don't know if you can shed light on it before you move away, before we call it a day, sir.
Okay. No problem. This is the graph of modulation transfer function against spatial frequency. Spatial frequency is just the number of line pairs, use line pairs per millimeter for any imaging modality. Any imaging modality. For this, we are looking at fluoroscopy. Looking at we have compared II with film. We have compared II with other optics. Also compared it with a system that uses a TV system that uses a 525 line pairs, and one that uses 1023 line pairs. I said for started with this. I said, for example, want to look at this one cycle per millimeter spatial frequency minus spatial frequency is 1 over 2 this, where this is the object size. The object size. You have that. So it means for this, if you have a spatial frequency 1 over 2 delta is equal to 1 here, we're looking at this. Want to look and get the thickness or the dimensions of the object if the spatial frequency is 1. We have that as 1 over 2, blah, blah, blah. So this is this mean, this is 1 over 2, and then we have 0.5 millimeter. So we have seen that 0.5 millimeter is the thickness or is the dimension of the body. Then I want to look at, want to compare it with all these other, this, and this. We look at this, for this one that has this, the value is here. If we go here, it has a higher value. So it means 1023 has a better discrimination of an object that is 0.5 millimeter. If an object is 0.5 millimeter, this one will better discriminate it. It will clearly show it as very, very distinct from surrounding objects, surrounding structures than this. Likewise, according to this graph here, is around 80, which has a better performance than this for this object. P is up there. If you go to a special frequency of 2, if it has 2, we end up getting the delta to be 0.25 millimeter. The same thing happens for this 0.25. We're going to have a value here, maybe 20, or 1023. We're going to have maybe 40 for II. For II, it is close to 80. For fin, it's above 90 or close to 100, as the case may be. So it means this, of course, still has a higher MTF. So it is going to have a better discrimination of this object, which is at 0.25 per millimeter. This is going to give a better discrimination of this object. This one is very, very low. So this one is not going to fully resolve it. But if you look at this graph, at this point, this one crosses the x-axis, this cycle per millimeter axis. So this is the limiting portion, the best this one can resolve here. And if you can get the value of, you can get this value here. So what, in this case, want to see the best this value, this guy can resolve, this 525 and TV line can resolve. So we have 1/2 is 3. So it means 6, this is 1. So that is 1/6. So that's what? 0 .10, 1 in 30. That's 6 times 4, 28, 20, and 20, 6 and 20, 3, 6 and 3. So 0.25 millimeter. So if an object is less than 0.14 millimeter, this one won't be able to resolve it. A TV line like using 525 won't be able to resolve it. Likewise, this one will be able to resolve it very well. This one excellently, very well too, excellently well. If you take it up, continue up, you can always have this. But here it is almost 0. The MTF is almost 0. Here for this, the limits, this one is 5 cycles per millimeter. You can get the corresponding what's it called, object size. Assuming we get the corresponding object size at 0.05 millimeter. It means if an object is smaller than 0.05 millimeter, this system wouldn't be able to resolve it. So that is it. So as the spatial frequency increases, that is, as the body becomes smaller and smaller for all the machines, for all the whatever, the MTF continues to reduce. I don't know whether you was able to do something.
Yes, sir, it's better now.
Okay.
I got the explanation. Thank you, sir.
Are you welcome?
So increase in spatial frequency reduce the MTF.
Yeah.
Okay.
As increase in spatial frequency. It means as an object becomes smaller and smaller, as the size of an object becomes smaller and smaller, the spatial resolution, which is determined by the MTF, reduces. The MTF is just the modulation transfer function, which helps us in quantifying the spatial resolution of an object, of a machine, of an imaging system. So as the object becomes smaller and smaller, the spatial resolution continues to reduce until it gets to a particular value where that system wouldn't be able to resolve it again. It's just something can just disappear. We wouldn't be able to say this something. We wouldn't be able to see it again. Okay.
Yeah, thank you, sir.
You're welcome. Okay. Sometimes we call it a day. If no other question. Okay. You have a wonderful rest for those who are not on call. For those on call.
Thank you, sir.
I want to wish you the best. Okay, now. Bye-bye.
Thank you, sir. Bye, sir.
Yeah.